This video is going to discuss the fundamental theorem of calculus part 2 and some specific applications of it. So previously we may have seen some definite integrals, and the fundamental theorem of calculus part 2 particularly is really nice in that it allows us to have an algebraic representation of that definite integral. Okay, so here's its statement. So f is a piecewise continuous function, so continuous, such that its derivative, so that the little f is derivative of big F. So in other words, the derivative of big F prime, or the derivative of big F, is little f. Okay. Then in that case, if we want to find the definite integral, what this is saying is take the so again, f is the antiderivative. Okay, antiderivative evaluated at x is equal to b, and then subtract the antiderivative evaluated at x is equal to a. Okay, so compute the antiderivative and then take the difference of the antiderivative value at the upper bound and the lower bound. Okay, so let's see some of this in action. So examples, working through this, the antiderivative, well, let's see, using proper mathematical notation, this would be equal to, find the antiderivative, increase the power by 1, constant stays up front, divide by the power, subtract off, and then this is another power rule, so x squared over 2, and I'm going to use a vertical bar to denote that I still have yet to do the evaluation, so 1 and 4. Okay, continuing, just simplifying this for my ease, x cubed minus x squared over 2, and I still have yet to evaluate it, so bar 4 and 1. Okay, and now I can go ahead and do the evaluation. So 4 cubed is 64, squared is 16, minus 2 is 8, so this is going to be 64 minus 8, and then subtract off, okay, whatever I get when I put in 1. So 1 minus, and then 1 squared over 2 is 1/2. Okay. 64 minus 8 is 56. 56, and then, so it'd be 56 minus 1/2, or 55.5. Okay. And that is the proper mathematical form for this. Okay. The next one, 4 over x dx, well, let's see. This is the same as the integral from 1 to e of 4 times 1 over x dx. Okay, so 4 is left alone. The antiderivative of 1 over x is the natural log of the absolute value of x, and I have yet to do the evaluation, so 1 to e. Okay, so now I can do the evaluation. This is equal to 4 natural log of the absolute value of e minus 4 natural log of the absolute value of 1. This is ln of e is 1, so this is just 4, and then natural log of 1 is 0, so the answer is just 4. Okay. A couple notes is, be sure, if you have yet to do the evaluation, be sure to include the evaluation bar, and you can go ahead and keep the bounds as they are. That's okay mathematically. If you simplify the function inside the integral first, that is fine. Just make sure that your notation communicates it. Okay. First application that we're going to see is if we're given a velocity function. Okay, velocity function. There's actually two different quantities that we can discuss in relation to position. So again, the antiderivative of velocity is position, but if we evaluate it just as normal with a definite integral, we get displacement. Okay, so we just evaluate it as normal, don't worry about anything. That's displacement. Okay, if we're concerned with total distance traveled. That's actually the integral of the absolute value. And so what we actually have to do is, since it's an absolute value, I need the velocity function may be positive in some areas and may be negative. Okay, so break it up into positive and negative areas. Okay, find the antiderivative, or compute the definite integral over each of those areas, and then add them up in an absolute sense. So don't worry about signed areas, just add them all up. Okay, so as an example here, I have a car's velocity function is given by, and here's the function, absolute value of t minus 2 minus 1, which is equal to this. Okay, find the displacement and total distance traveled over 0 to 5 hours. Okay, well, I always like to start with a picture, okay, to see what's going on here. Okay, so here is a diagram of the picture. I believe we saw this in a different video, but so what I can do is, for displacement, I'm fine. I don't have to worry about anything. But for the case of total distance traveled, I need to be concerned with positive areas, which I'm coloring in green, and negative areas, which I'm coloring in purple. Okay, I need to break it up. Alright, so to do this thing, to find displacement, okay, displacement is going to equal the integral of from 0, okay, here are our bounds, 0 to 5 of v of t dt. Okay, and now since this is an absolute value graph, I actually have to break it up into these two cases. So this is going to be from 0 to 2 of negative t squared, and this should actually all be in brackets, t squared, t minus 2 minus 1 bracket dt plus the integral from 2 to 5 of, and I'll do a big bracket here, t minus 2 parentheses minus 1 dt. Okay, and so if I do this out, 0 to 2, simplifying this, which I like to do, it'll be minus t, and then it'll be plus 2 minus 1, so plus 1 dt, and then plus the integral from 2 to 5, and then this is going to be t minus 3 dt. Okay, find the antiderivative of each of these and do the evaluation. So this is equal to minus t squared over 2 plus t, evaluated that part from 0 to 2, plus the antiderivative of this, so this is t squared over 2 minus 3t, evaluated from 2 to 5. Okay, doing the evaluation here, t squared, okay, so 2 squared is 4, negative 4 over 2 is negative 2, plus 2, okay, so this part is going to cancel out completely. 0 I don't have to worry about because that'll be 0. Okay, plus, and then this part, so it'd be 25 over 2 minus 15, and then I have to subtract off whatever I get in the lower bound case. So 2 squared is 4 over 2 is 2 minus 6. Okay, so this is going to wipe out, and I'm going to be left with, okay, 25, that's 12 halves, so this is minus 2.5, and then this is going to be a minus a negative 4, which is just going to be positive 4, so this ends up being 1.5. So displacement here is 1.5, and we did it say meters? I forget. Kilometers. Okay, so that would be its displacement. Now, for total distance traveled, that's where it gets to be a little bit longer in the sense that we have to break it up into 3 chunks now instead of 2. So I need to compute the integral, so total distance. I need to break it up so that it would normally be the integral from 0 to 5 of the absolute value of v of t dt. But this now breaks up as from 0 to 1, because that's a positive region of v of t dt, plus, and then the negative region, so from 1 to 3 of v of t dt, plus, and then 3 to 5 of v of t dt. Okay, and again, we have to break it up because it's positive or negative areas. Okay, so now going ahead and computing this, we found earlier that this is 0 to 1, and then the function side here simplifies to t plus 1 dt. Now this is actually an interesting case. I need to actually break this up into 2 integrals because that's where the function changes. So, and here the one thing that I forgot to include is, since this is a negative area, I actually need the absolute value of this. So plus, and then it's going to be absolute value, break it up into the 2 pieces from 1 to 2, negative t plus 1 dt, plus, and then it'll be from 2 to 3 of t minus 3 dt, all absolute values, and then plus integral 3 to 5 of t minus 3 dt. Okay. Now going ahead and computing this, we can find the antiderivatives. Okay, so this is minus t squared over 2 evaluated, and I forgot the other part. Let's go back and add that. Negative t squared over 2 plus t evaluated at 0 and 1 plus, and then this is the absolute value of this whole thing, so it'll be negative t squared over 2 plus t evaluated at 1 and 2 plus, and t squared over 2 minus 3t evaluated at 2 and 3, all absolute values, and plus t squared over 2 minus 3t evaluated at 3 and 5. And I encourage you to do this at your own time, but what this ends up being is equal to, once you do the evaluation, 1/2 plus the absolute value of negative 1/2 minus, or plus negative 1/2, all in absolute values, plus 2. And so this ends up being negative 1 inside the absolute value, positive of all of that is 1, so it's 3.5 would be the total distance traveled, but remember the units, 3.5 kilometers. Okay, so again, the calculations here can get to be a little extensive, but power through. Alright, and then the last application that we want to discuss in this video is the average value of a function, and this is its definition. Okay, so the average value of a function, we have to do 1 divided by the difference in the bounds, and then compute the definite integral of the function. Okay, so as an example here, we have a heartbeat oscillates periodically, and we're given the function for heartbeats. Determine the average number of heartbeats from 0 to 8. So the number of heartbeats on average is equal to, according to the definition of average value, 1 over 8 minus 0, integral 0 to 8 of the function 130 plus 15 cosine of pi t over 6 dt. Okay, and now I can compute this integral, so this is equal to 1/8, and then the antiderivative here is 130t, and then cosine is the derivative of sine plus 15, and then pi t over 6 divided by pi by 6. Okay, and I still need to evaluate all this at 0 and 8, and then that'll be my average value. Okay, so 1/8. I'm just going to simplify this for my own sake. 130t. Dividing by pi over 6 is the same as multiplying by 6 over pi, so 15 times 6 is plus 90 over pi sine of pi t over 6, evaluated 0 and 8. Okay, and now I begin the evaluation process. So 1/8. Okay, then I plug in 8. This is going to be 130 times 8 plus 90 over pi sine of pi 8 over 6. Okay, all of that minus 130 times 0 plus 90 over pi sine of 0. Okay, so this whole last term drops out, because sine of 0 is 0 and 30 times 0 is 0. Okay, so that whole thing drops out. Okay, so now I can do the calculation. And doing the calculation here, this ends up being 1/8 of, and this is approximately 1015.19, and then performing the last stage here, this is 126.9, and so that this is an average number of heartbeats, so make sure to include units. Okay. So, in this video we discussed fundamental theorem of calculus, which says for a definite integral, all we have to do is compute the antiderivative and then compute and evaluate the antiderivative at each endpoint of our interval and take the difference.